If an alien space traveller had flown past the Earth 150 million years ago, it would have looked quite different from how it looks today. It would have looked like this. At that time, South America and Africa were joined together, and India was tucked up close against Africa. If the alien had come back 70 million years ago, it would have looked quite different again. It would have looked like this. South America and Africa have separated now, and India is an island in the middle of the Indian Ocean. The great characteristic of our planet is that the continents move around, and we haven't known for very long that they do so. Today, what I'm going to do is tell you the story of how we came to know about all that. What's happening on the surface of the Earth is so strange, it's so bizarre, that if anyone had been standing here in 1950, say, giving this lecture, and saying what I'm about to say, people would have thought they were completely mad. They would have been labelled just as a crank. Yet what happens at the surface of the Earth really is strange, and it's true. What we're going to do is to look at the evidence for it. This is the big story in earth sciences this century, maybe in earth sciences ever. And it's a story of exploration, of the exploration of the oceans. And it was all over really quite quickly. It took about 20 years between about 1950 and 1970. That's all. And why the exploration of the oceans? Because it turns out that the key to understanding how the continents moved around was at the bottom of the sea, where no one had thought to look. No one knew much about the oceans until after the Second World War, the United States Navy became interested. And they became interested because of submarines. Submarines dominated naval warfare, and the Navy was desperate to know what was underneath the sea, not just on top of it. So they poured vast amounts of money into exploration of the oceans. And the thing they were most interested in was what was the water depth. What did the sea floor look like? And what they found was truly amazing, far more improbable than anyone would have guessed. This is a map of the seafloor with the water taken away. And what they found in the 50s was this. There were huge chains of mountains. These are the longest, most continuous ranges of mountains in the world. They are going down the middle of the oceans on the whole, like the middle of the Atlantic Ocean, and through into the Indian Ocean, the Pacific Ocean, and up here. These mountain ranges are 20,000 kilometers long. The mountains in these ranges rise above the seafloor higher than the highest peaks of the Alps. These things became known as mid-ocean ridges because they are in the middle of the ocean, like here in the middle of the Atlantic. The other thing they found was deep, deep slots or gashes around the edges of the continents, like here around the edge of the Pacific Ocean and here the west of South America. These deep slots were so deep you could bury Mount Everest in these easily and not notice them. These things became known as trenches. As they sailed around taking these surveys to see what depth the water was, they also found out something else which was very strange. As they went, they picked rocks off the seabed with a kind of bucket, or dredge as it's called, to bring up rocks from down below. And as well as finding sediments, sand and mud, which you would expect, they also found lots of this stuff. This is a black volcanic rock. And it doesn't look at all like the kind of rocks you see on the continents, which generally look like this. This is a typical rock from the continents. And people, I suppose, if they'd thought about the seafloor at all, thought, well, maybe the seafloor's are bits of sunken continent. But they didn't really look like it. And the other strange thing is that continental rocks are known to be very old. Continental rocks can be as old as 4,000 million years old, nearly as old as the age of the Earth. But the oldest rocks anyone ever found on the oceans were much, much younger. They were only about 200 million years old. So there's a big difference. The ocean seemed to be very young, but nobody understood why. What happened next was people thought, well, let's go and measure the strength of the magnetic field behind the ship as we chug along. And they developed an instrument to do that. Now, let me show you what I mean by the strength of a magnetic field. What we have here is a coil, and this coil of wire, if we put an electric current through it, will make a magnetic field, and Bryson is doing that now. And that magnetic field is attracting this iron weight and pulling it down. And we can measure the strength of this magnetic field by how it's pulling this scales down, or this balance. Now, chugging along behind a ship, we don't use anything as crude as this. We have much more sophisticated instruments, but the idea is the same. People wanted to measure the strength of the Earth's magnetic field. What a strange thing to want to do. Why should anyone want to do that? Well, at that time, no one knew anything at all about the oceans, and they thought, well, let's measure anything we can. And the Navy thought, well, if you want to measure that, you can measure it, but as long as you keep measuring the water depth. What they were really interested in was the shape of the seafloor. So interested that actually a lot of those surveys of the depth of the seafloor were classified. They were marked secret, and you couldn't talk to anyone about them. Now, when these people sailed around measuring the strength of the magnetic field, what they actually measured was quite astonishing. Let me show you. Here is a map of part of the ocean. And this is the coast of western North America here, Canada and California here. And what they did in their ships was this. They steamed backwards and forwards in their ship like this on a sort of zigzag track to cover the whole seabed. And as they went, they were measuring the strength of the magnetic field. What they found was this kind of thing. Here we are. The ship was steaming along this direction, and as it went, it measured the magnetic field, and they found it was strong in some places and weak in other places. It varied. The strength of the field varied as it went along. And they found this everywhere. Here's a track which is about 300 kilometers long. What are we going to do with that? How can we put that on a map? We don't want a map which is completely covered in wiggles. Well, the first thing we can do is draw a line through the middle, an average, if you like. And let's do that. Here is a line which goes through the middle of this. And how are we going to represent that on our map? What I'm going to do is this. I'm going to say, well, in some parts of this, this track, the magnetic field is greater than average, and in other parts it's less than average. Where it's greater than average, I'm going to draw a black dash like that. So there and there. There's another place it's greater. It's greater along there, a little bit there, a little bit there, a little bit along there. Then what I can do is I can turn this map of tracks into a series of black dashes all the way along. And what you find then is really very remarkable. If I take this off, what you find is this. Along this track here, I would see black dashes, black, 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 and then also along here. And you find that the black dashes line up. There's a black dash there, and here, and here, and here, and here. And you can join them up like this. So what we were seeing on the seafloor here was a pattern of stripes. Stripes where the magnetic field was greater than average, or stripes where the magnetic field was less than average. And this is actually real data. This is not just a schematic picture. This is a real profile. And this is a real map of what people found. This is just part of a much bigger survey. Let me show you what the real survey looked like, which is over here. This is a map of the Northwest Pacific. The border between Canada and America is about here. And this was a pattern of stripes over the seafloor. And this was a very big survey. The length of this picture is about 1,000 kilometers, and it's about 500 kilometers across. And on the seafloor was this extraordinary pattern of stripes. What on earth could this mean? The thing about these stripes is that they look very regular. Can't just be coincidence. This is such an extraordinary pattern that it was like seeing writing. It was like seeing a language, a hidden script of some sort on the seafloor. But the trouble is, no one knew what it meant. No one could speak this language. What were they to do about it? What's important, though, is that although no one knew what it meant, no one thought it was unimportant. It was going to take 10 years to sort out what this pattern meant. Now, it wasn't just in the oceans that people were looking at magnetism. Magnetism was a popular thing to look at in the 1950s, and people were also doing it on land. And in particular, they were looking at magnetism in rocks. Now, volcanic rocks in particular form, like this one here, this is a volcanic rock. Volcanic rocks form from molten lava, which erupts at the Earth's surface and then cools. And the rock contains little tiny grains of iron oxide. And when they cool, they become magnetized. And they become magnetized in the direction of the Earth's magnetic field. And then the rock itself can become a little magnet. Let me show you that this rock here is a little magnet. Here's a compass needle pointing north at the moment. I can actually make it move by pushing this magnet around. So rocks can become magnetized. Now, volcanic rocks that form today become magnetized in the direction of the Earth's magnetic field today. That's what you would expect. But some magnetic rocks, or some rocks, were magnetized apparently backwards. Let me explain what that means. Here is a bar magnet, and the Earth's magnetic field looks like that from a bar magnet. Now, if I produce this, this is a magic wand which has another magnet in here, and this magnet can move around here. If I bring this magnet close to this magnet here, move it around, you'll see that the yellow end of my wand is pointing to the red end of this magnet. Now, if I reverse the magnetic field in this sample here, so supposing this was my rock with a magnet inside it, when I say it's reversed, magnetized backwards, what I mean is it's like that. Now, instead of the yellow end of my magnet pointing to that, the red end will. So that's what I mean by being magnetized backwards. It looked as though the magnet in the rock was pointing in the different direction from the Earth's magnetic field. It was pointing the other way. Now, we don't measure the direction of the magnetization in rocks by this kind of magic wand. We use a much more sensitive instrument, which is like this thing here. And if I show you this, how this works, I'm going to bring up this rock, which is like a tiny little magnet, towards the end of this probe. And we should see that needle on the screen move. There it is, it moves to the right. And if I turn this up the other way, it'll move the other way. So that this instrument can tell what direction the magnetization is in my rock, what way up the magnetization is. Now what we have here is 6 rocks, which are all from a volcano in Britain. These are from a volcano in Scotland, off the west coast of Scotland, the island of Skye. And they're from, that volcano was active about 50 million years ago. It's not doing anything now. These are old lavas. Now the extraordinary thing about these lavas here is when we measure the direction of the magnetic field in them, they are backwards. The magnetic field is in the opposite sense from the magnetic field of the Earth. And these are much less magnetic than this rock over here. They're very weakly magnetic, but this can still pick it up. Let me show you. You'll have to watch the screen very carefully now because the movement will only be a small amount. So if I bring this one close to the probe here, so it just moves very slightly. And if I turn it over, it moves very slightly the other way. It's a small effect, but these instruments are very, very sensitive. And we can actually measure the direction of magnetization in these rocks. So what are we to make of all this? Some rocks are magnetized in the direction of the Earth's magnetic field, and some are magnetized backwards. Well, the next advance in this whole business was to actually be able to date these rocks, to find out how old they were. And in the late 1950s, some instruments were developed which could actually work out how old those rocks are by looking at the natural radioactivity in them. These rocks, as I say, are 50 million years old, and their magnetization is backwards. If we take other rocks from some other part of the world, Japan maybe, or America, or India, doesn't matter, if they are the same age as these rocks, you find that they are also magnetized backwards. And if we find rocks which are magnetized in the normal sense of the Earth's magnetic field, all other rocks in the world of the same age are also magnetized in that same direction. So it really does look as though the magnetic field of the Earth itself flipped, that the North Pole became the South Pole magnetically, and that the South Magnetic Pole became the North Pole. And by dating these rocks, you could find out when that happened. And by about 1966, people had made a calendar of what had happened. And this is the calendar. What we have here is time. This is today, 0, 1 million years, 2, 3, 4 million years. And the black means that the magnetic field is in the same direction as it is today. But here, which is about 700,000 years ago, the magnetic field flipped. The Earth's magnetic field turned round. And here, just before 1 million years ago, it had flipped back again. And here it was reversed, and here it was reversed, normal, and so on. It had changed with time. And what this thing tells us is when it happened. This is a calendar of when the magnetic field reversed. Now, is that what's actually going on? Let's remind ourselves about the Earth's magnetic field. In the last lecture, we talked about the magnetic field, and we showed that the Earth's magnetic field originated in the core, where there was liquid iron that was moving around. That liquid iron was able to generate both the magnetic field and also electric currents. Now, this thing here is a self-exciting dynamo, which we used last time to demonstrate how you could make both a magnetic field and an electric current at the same time. I'm going to need 2 volunteers. Aha. And I think I'll have, yes, you 2 there. Yes, you 2. Okay. Thank you very much. What is your names? Richard and Edward. Well, Richard, you come this side here, and Edward, you come this side. You know what you're going to have to do? Hold on to the handle. I want you to turn it that way round. Right, and you have to... Oh, derailed it. Perhaps a little more gently. Let's try again. Okay. So by turning this thing, you are generating both an electric current and also a magnetic field. What's happening is we're moving iron, which is a conductor, around in this coil. Now, one of the extraordinary things about this dynamo is it doesn't actually matter which way the electric current goes. If I ask Bryson to set it up going the other way, keep going. These 2, my 2 assistants, are still turning the hand in the same direction, but this is quite happy to make an electric current go in another direction. And when the electric current reverses, the magnetic field this is making is also reversing. Thank you very much. Now, this is a rather remarkable property of self-exciting dynamos. They don't care which direction the electric current goes in. You can go in either. But of course, if it changes direction, so does the magnetic field. It looked then as though it happened instantaneously because I asked Bryson to just set it off in the other direction. In the Earth, where the dynamo is from fluid motions in the core, we're not quite sure what makes it change, but we do understand that it can change because the dynamo doesn't actually mind which direction the magnetic field goes in. In the Earth, it doesn't change instantly. We now know it takes about 10,000 years, in fact, for the field to die away and then start up in the other direction. But geologically, that's as good as instantaneous, and we're not going to worry about that. So that the final result of all this work on land, looking at these magnetic rocks, magnetized rocks, was to produce this calendar. Now, how does this calendar help us understand those stripes in the oceans? Well, what happened next was really a big breakthrough. It's not very often in the history of science you can say, yes, that was the moment when someone produced the theory which sorted it out. It's normally something which happens more gradually. But in this case, that did happen. It was in 1963, and the breakthrough came by 2 people who were at Cambridge, 2 scientists at Cambridge. This person, Fred Vine, who was a graduate student in Cambridge at that time. He was in his 20s, and he was working with another person, Drummond Matthews, here. Now, Drummond Matthews here is sitting at the back of a ship with a huge grin on his face. He's just piled up 1 ton of high explosives into a big heap here, which he's about to throw off the back of this ship and make the most enormous bang to send sound waves through the seafloor. And he's grinning from ear to ear because everyone likes letting off big bangs, even famous scientists. Now, what did these 2 say? They said that perhaps the way the stripes are made is something to do with these ridges, these chains of mountains down the middle of the oceans, the mid-ocean ridges. They said, well, perhaps what's happening is that those ridges are making lava, molten rock is coming to the surface, it's cooling, and when it cools, it lines up in the direction of the magnetic field at the time that the lava's formed. But they did it in a really rather special way. And let me show you. I'm going to need some helpers here. I'm going to need 8 people. Now, let's have you 2, please. We'll have you 3. It's 5, 6, please, and you 2, 8. Now, all come down here, please. come around me. I like 4 on this side, so let's have 1 more on this side. Over here, please. And 4 on this side. Okay? And I'm going to show you what happens at a mid-ocean ridge, or what Vine and Matthews thought happened at a mid-ocean ridge. Will you come back here, all of you? Right back here. Now, the first thing I'm going to have to do is to turn you into molten rock, into magma. So get down, please, crouch down on the floor. And I'm going to explain what happens. Can I have my first 2 pieces of magma? That's you and you. You come here. I'm going to turn you into rock. So you stand up now, and you've become rock at the surface. And now, because you are rock that is formed in the present day magnetic field, I'm going to give you black hats. And now I'm going to make some more rock from my magma. So I need 2 more magmas, please, you. And you're going to turn into rock too. And now the magnetic field has reversed. So I'm going to make you wear white hats. And I'm going to add you to the seafloor, but in this rather special way. I'm going to ask my first 2 to just step to the side, 1 step, like that. And you are going to fit in between them, like that. Thank you very much. And now I need my next 2 people, please. And when you form, the magnetic field is still reversed. So I'm going to make you wear white hats. And I'm going to make you join our new bit of mid-ocean ridge by moving you sideways and putting you 2 in the middle like that. And may I have my last 2 pieces of seafloor, please? You come here. We've just turned you from magma into rock. And now the magnetic field has reversed again. And so I'm going to make you wear black hats because you're magnetized in the direction of the Earth's magnetic field. Move sideways, please. Thank you very much. What have we done here? We've made new seafloor. I'm the ridge here. We've made it in equal amounts on both sides. And we have the same pattern of magnetism on both sides. It goes black, white, white, black on this side, and black, white, white, black on that side. The idea here is that new seafloor is formed by spreading, and that we have exactly the same pattern of magnetic stripes on both sides. Thank you very much. You may return to your seats with your hats. Take your hats. The important thing there in that demonstration was that when I introduced the new magma, the new people at the middle of the ridge, the other ones didn't change their hats. The rocks have memory. And that was supposed to be how the stripes formed. Well, at that point, this theory, which Vine and Matthews had produced, was really extraordinary. In fact, it was so extraordinary that they didn't believe it either. They thought, well, this is just, a nice idea. They didn't believe it. No one else believed it either. That was it, really. And one of the reasons they didn't believe it is they couldn't think where to test it. The obvious way to test it is to see if the pattern of stripes was the same both sides of the ridge. Now, this famous survey in the Pacific Ocean here with the stripes, they thought, well, we can't test it there. And what they didn't realize was that right in the middle of this pattern of stripes, there was indeed a mid-ocean ridge. The reason they didn't realize it was because the Navy had made all the maps of how deep the water was secret. So they couldn't know about it. But by 1966, Fred Vine had actually managed to find out that there was indeed a ridge in the middle. And here is where it is in red here. So this was the ridge in the middle. And what he showed by coloring in the stripes was whether the pattern was the same on both sides of that ridge. So the next stripes here, which are shown in orange, you can see the orange stripes are the same distance from the ridge on each side. And the next stripes, which are shown in yellow, they are also the same distance. And the next ones, which are in green, they are also equidistant from the ridge, and so on as we fill in the pattern. So it really did look as though the stripes were the same pattern on both sides of the ridge. And it wasn't just in the Pacific he found this. By that time, there was another survey across the range of mountains in the middle of the Atlantic, south of Iceland. This is the survey in the middle of the Atlantic. And once again, there's a ridge down the middle in red. And if we color in the stripes either side, they're the orange stripes, and now the yellow stripes, green stripes, and so on as we go outwards. Each time, the next stripe is the same distance from the ridge. This is another symmetrical pattern. And it was actually even better than that. If you remember, the way we made the stripes was from these wiggles. And this, in fact, was the true data. This is the real profile of the wiggles that actually, in the end, convinced everyone. Here is the wiggles going across a mid-ocean ridge in the South Pacific. Here is the ridge with the high mountains here in the middle. And these are the pattern of wiggles either side. The most extraordinary thing is how precisely they are the same on each side, wiggle for wiggle. Let me show you. Now, it's not a perfect fit, but it's pretty good. And this, as I say, is real data. This is not a fiddle. This is the actual profile that they saw. And this was about 300 kilometers long right the way across. It actually matched very well. But it was even better than that. What they found, which was so extraordinary, was that if we took our calendar, which we had before, the calendar of where the magnetic field in the Earth reversed, it matched the wiggles precisely. If I put it there, the wiggles are above the line where the field is the normal orientation, in other words, black, and the wiggles are below the line where the field is white. So we had the same sequence of magnetic reversals on land that we had in the ocean. And furthermore, you saw the same sequence all around the world. All mid-ocean ridges had exactly the same sequence. And we can use this sequence of stripes to show how fast the ridges are spreading. So here, for example, we know that out here it's 4 million years old, and this seafloor was made at the ridge over here, and in 4 million years it's gone that far, which is about 150 kilometers, I think. And so we can show that this ridge is actually spreading at about 9 centimeters a year. We can work out how fast the seafloor is being produced. So Vine and Matthews were right. The surface of the Earth is being made by seafloor spreading at ridges. That's what's going on. The thing is, if the seafloor is being created all the time at ridges, what's happening to the Earth? Is the Earth just getting bigger and bigger and bigger and bigger? Is it just puffing up like a great big ball? Well, that doesn't sound terribly likely, doesn't sound very probable that that would happen, but let me give you another reason why I really don't think that's what's going on. This balloon is supposed to represent the Earth. So here is the Earth. Now, sitting on top of the Earth, as we know, are continents, and this red curve is supposed to be a continent. This could be, for example, North America, let's say. Now, you can see the problem North America is going to have if the Earth really inflates, if it gets bigger and bigger. Let's ask Bryson for a bit of puff here. So here we are, inflating the Earth with lots and lots of seafloor spreading, making lots and lots of new seafloor, and the Earth has got bigger and bigger. That'll do, I think. And if we actually now see whether the continent will fit, it doesn't fit. You can see now, because the curvature of the Earth has changed, the continent sitting on top can't fit. It would have to break inside. It would have to change and break up in order to fit the new curvature of the Earth. And that's not what we see. If we look at the middle of continents like America, they haven't broken up at all. So I don't like that model. We'll get rid of that. If we're not going to make more and more surface area of the Earth, if the Earth is not going to expand, then we've got to find some way of getting rid of the Earth's surface. We're making new surface at the mid-ocean ridges. Let's find some way of getting rid of it. But where? How does it happen? Well, the solution to this mystery actually came from a totally different direction. Another big concern of the 1950s was this kind of thing. What we're looking at here is a nuclear explosion. This is an atom bomb let off in the atmosphere in the 1940s. Big mushroom cloud going up in the air. And what's going up in the air is lots and lots of radioactive fallout, lots of radioactive dust, which is falling back to Earth, and people were very worried about this in the 1950s. It was a form of pollution nobody wanted. And what was going to happen, for sure, was that there was going to be a treaty which banned this. Everyone could see this was coming, and by 1963, there was a treaty which forbid the letting off of explosions like this in the atmosphere. You had to do it underground. Now, it was the job of the United States Air Force to actually monitor what was happening in Russia, and what they wanted to know was how were they going to check on what the Russians were doing underground with their explosions. The obvious way to watch what the Russians were doing was to listen to the sound that these explosions made in the Earth. How do we do that? We do that with this. This is a seismometer. It's really an extremely sensitive microphone that listens to vibrations or sound waves in the earth. Let's see how it works. Now, I need some volunteers, please. And I'll choose you, please, over there. Now, can you stand up, but don't move for the moment? And everyone else, keep absolutely still, no fidgeting around. Now, I want you, please, to walk down the stairs, and as you walk down, we're going to look at this screen here to see what happens. Okay? Come down the stairs, please. Thank you. And what is your name? Eleanor. Now, Eleanor, I'm going to make you be an explosion. I want you to jump up and down a few times. Jump up. Thank you very much. Let's do it one more time, even bigger, please. Can you make some even bigger jumps? Go. Yeah, that's better. It's gone right off the screen now. Thank you very much. Now, what I want you to do is to turn round and now to go back to your seat, clumping up the stairs as hard as you can go. Thank you very much. You've been a good explosion. Now, the United States Air Force was extremely keen then to listen to these explosions that were coming out of Russia. But at that time, listening to sound waves in the earth, the science of seismology, was in a real mess. There were instruments all over the world, but they were all different. Some of them didn't work. Some of them were wired up backwards. They were run by people who didn't really know what they were doing. And they wanted to encourage work in listening to the sound in the earth. So what they did was install instruments all the way around the world of the same type. They put in fact, 120 in order to listen and collect good information about sound in the earth. So why am I telling you all this about nuclear explosions? Because if you actually do this, if you put instruments in to listen to nuclear explosions, you also, of course, pick up earthquakes. And there are thousands and thousands of earthquakes every year. What we actually pick up is about 20,000 earthquakes every year in the earth. And the problem the Air Force had was, how are you going to tell the difference between these explosions and the earthquakes? Well, one way to tell the difference is simply to see where they are, to locate them, to see where the sound is coming from, because if the sound is coming from the Pacific Ocean or America or whatever, it's clearly not coming from Russia and it can't be an explosion. So the first thing we got out of all this effort was the first accurate maps of where earthquakes occur. And what you're seeing on this screen, these flashing lights, are earthquakes happening all the way around the world. Okay, so we could actually see accurate maps of earthquakes. Well, why are we interested in earthquakes? We're interested in earthquakes because earthquakes happen when rocks break or when they slide past each other. In other words, earthquakes are telling you that the earth is deforming in some way. And if we look at this map now, I want to look at the Pacific region here. Here's the Pacific, where lots and lots of earthquakes happen, and all the biggest earthquakes in the world happen in the Pacific. What we're showing you is just 10 years' worth of earthquakes. There are huge numbers of earthquakes in the Pacific Ocean. And mostly they occur around the edge of the Pacific, as you can see, and in particular they occur near the trenches, which are those deep, narrow slots, so deep you can bury Mount Everest in them. So these earthquakes mean that faults are moving. What sort of faults are actually producing these earthquakes? And what we're going to look at next is actually this region up here, which is the region of Alaska. Because in 1964, very soon after we started to get this kind of information, there was an absolutely enormous earthquake in the trench off Alaska. And in the next picture here, I'm going to show you what it did. The earthquake produced lots and lots of damage. It made the earth wobble for months. But it did also something very interesting. This picture here shows the coastline in this part of Alaska after the earthquake. The high tide level is here now, but before the earthquake, the high tide came right up to here. This huge bit of seafloor here has just been lifted out of the sea. The next picture shows a detail of what that coast looks like. Here's a man with a pole which is a few meters long, and the sea is at high tide level here, but the old high tide level was right up here. And what the white colour is barnacles, little sea shells which used to live underwater, which are now killed by being lifted out of the water in this earthquake. And this last picture is actually a jetty. It's a harbour jetty for a Coast Guard boat, and the jetty is completely useless. This is now dry land underneath this jetty, as this harbour was lifted out of the water by several meters. So what sort of faulting then was responsible for this earthquake? And to look at that, we have a new demonstration. What happened in this earthquake was this. And this is the Pacific floor. This is part of Alaska. And here is the trench. This is the deep, narrow slot along the edge of the Pacific, which is called a trench. Now, I'm going to ask Bipin to make the Alaskan earthquake. Okay, move. Very nice, thank you. These lights here show the fault that moved, or the sort of fault which moved in the Alaskan earthquake. What happened in the Alaskan earthquake was that the Pacific seafloor slid underneath Alaska. And by doing that, it actually lifted up some of the front of this coastal region here, pushed it up into the air. Let's make one more earthquake here. Thank you very much. This, in the case of Alaska, was an absolutely enormous fault. The fault, the length of the fault which moved in that particular earthquake was 650 kilometers long. That's a distance from here to Switzerland. And the amount it moved was 20 meters. That's more than the width of this room. And it moved in one go, something moving from 20 meters over there on top of something else. And it took a few seconds to do that over this enormous distance. This was an absolutely huge earthquake. But what it told us was this, was that the seafloor and the Pacific seafloor was sliding underneath Alaska. Thank you. And when we look at the other earthquakes around the Pacific, what you see is the same sort of earthquake all the way around the edge of the Pacific here. That everywhere around the Pacific, from Alaska through to Japan, past the Philippines, past the New Hebrides here, all the way down to New Zealand, everywhere along this part of the Pacific, we had the same sort of earthquake, where the Pacific seafloor was sliding underneath the land. This was the clue we were looking for. We know that the seafloor is created at these ridges here, and this is where it's destroyed, along the trenches. This, then, solves our problem. The Earth doesn't have to change its size. It can stay the same size because it can be destroying seafloor at the same rate that it's making seafloor. When we look at where the earthquakes occur in the world, nearly all the earthquakes occur either around the trenches here, around the edges of the ocean here, or they occur on the mid-ocean ridge systems, down the middle part of the oceans here, like the one down the middle of the Atlantic also. The earthquakes occur in these very narrow bands. Most of the world doesn't have earthquakes. If we come over here and look at a map of the world, what I'm drawn on here in white lines are simply the bands where you get earthquakes. These are and away from these white lines, you get very few earthquakes indeed. So these white lines are white lines where the Earth is deforming. That's where things are happening. And away from these white lines, nothing much is going on at all. What we've done here is we've produced about 12 different areas which are doing nothing, and lots of white lines where things are happening. We call these areas here, outlined by the white lines, plates. And if you look at the boundaries of these plates, you can see that they don't, in general, follow the boundaries of the continents. Here, look at this. This is Africa here, and the plate boundaries go right the way round Africa, but stay well away from the coastline. Same is true here for South America. And what we can do is actually split the Earth up into a series of these plates. And that is this next object here. So here we have an Earth, and we've put on it the plates. These are plates on the Earth which are outlined by the earthquakes. And looking at this, you can't really see where the continents are. You can't see the shapes of continents on these plates because the continents are not what's important. What's important is where the earthquakes are. So that's what's going on. What's going on in the seafloor is the seafloor is being created at ridges here. That's where seafloor spreading is producing new seafloor, and it's being destroyed in the trenches around the edge here. And in between, it's doing nothing. It's just moving from one place to the other place. The other thing, and these plates really, as they move around relative to each other, can only do three things. The plates can separate, moving apart, like they do at the ridges. They can move towards each other, like they do at the trenches here, where one plate slides underneath another. Or they can move sideways past each other. And the most famous place this is going on is in California here in the west coast of the United States, where the Pacific plate is sliding past North America. And that motion is happening on one of the most famous faults in the world, the San Andreas Fault. Let's have a look at it. This picture here is a picture of the San Andreas Fault in California. What we're looking at is a river. There's a stream coming off the back of this slope out towards the front. But right across the middle of this picture is a line, and that line is the San Andreas Fault, and you can see what it does to this river. The river comes down here, and then suddenly it jumps across the fault here. The background has moved to the right, and the foreground has moved to the left. And the reason for that is that this in the front is the Pacific plate, and in the background is the American plate, North American plate. And the offset of this stream, or the sideways movement of that stream, which is about 10 meters, happened in a big earthquake in 1847 in one go. So that's it. That's what the seafloor is about. These plates moving, and we can tell how fast the plates are moving from the pattern of stripes in the oceans, the magnetic stripes, and we can tell where the edges of the plates are from the earthquakes. That's all we need to know to see how the surface of the Earth is moving around. The extraordinary thing about this story is that every time someone went out to measure something they'd never measured before, or to look at something they hadn't really thought about before, like looking at water depth, like looking at the magnetic field of the Earth, like looking at where the earthquakes are, every time they did that, the whole story jumped. You found out a huge number of new things. And the final bit of new technology, which has really helped us, is this thing. What this is a box. It's a little computer, and this big yellow cable here is attached to an aerial on the roof. And the aerial looks like this object out the front here on a tripod. And what it's doing is listening to satellites. There are about 20 more satellites up in the sky, whizzing around the Earth, and they are sending information down about where they are, what their orbits are, what the time is on the clocks on board those satellites, and that antenna is picking up all that information. And it can use that information to say where it is. It can tell me where the antenna is. Well, I know where it is. It's in the Royal Institution. That's not much help to me. What is much more interesting to me, though, is this. We have another antenna identical to this on top of a building in Florida. Florida is the other side of the Atlantic Ocean. And what we can do is if we record the information here from the satellites and we record the information in Florida from the satellites, we can work out the distance, the precise distance between those two antennae with amazing accuracy. It takes about 2 days to do this. We have to listen to those satellites for 2 days. And they've been working out, the people who've been doing this for me, have been working out all morning what that distance is, looking at this information. And I don't know. I've not actually seen it. I think Bryson's has found out the answer now for me. And I will read out the answer. The distance between this antenna and the other one we set up in Florida, in America, is 6,793 kilometers, 291 meters, and 59 centimeters. So what, I hear you thinking? I said, and 59 centimeters. I mean, and 59 centimeters, not and 58 centimeters, not and 60 centimeters. We can measure that distance to within 1 centimeter, which is incredible that we can measure a distance of 6,000 kilometers to within a centimeter. The reason that's important is that the mid-Atlantic ridge, the band of mountains down the middle of the Atlantic, which is spreading, that's spreading at 2 centimeters every year. So I can go back next year and measure that distance, and it will be different. And we could use this to measure how fast the plates are moving. Now, I'm age 40. In my lifetime, the mid-Atlantic ridge has spread about that much. The Atlantic has got about that much wider since I've been alive, and that's actually one of the slow ones. The Pacific ridge is going about 5 times faster. So in my lifetime, it's actually the Pacific has got wider by about twice my height, or at least the mid-ocean ridge has spread by about twice my height. And we can use this technology to now measure the motion of the plates directly. We can do another very interesting thing, which is to measure the distance between points which are on the same plate, and what you find is they never change. They don't change at all. So the interior of the plates is completely rigid. All the plates do is move past each other. This whole view of how the Earth works with these plates moving around is called plate tectonics. Once we have this, we can actually then start to fit together all sorts of puzzles. We know that the mid-ocean ridges are made by spreading, by seafloor spreading away from the mid-ocean ridges, and we know how fast that's happening. If we want to see what it looked like before, all we have to do is run that conveyor belt backwards to see how it got like that. And now let's do that. Let's go over here and look at a map. This is how the Earth looks today, and now I'm going to run it backwards by just rewinding the stripes in the oceans. So here are the stripes in the oceans being rewound, and we're winding the continents back to where they were before the oceans opened. And the Atlantic Ocean is closed in the south, it's now closing in the north, and here is India tucked up in the corner against Africa. That is the picture we saw right at the beginning of the lecture, where I said, here's what the Earth looked like 150 million years ago. And there it is actually still looking like that 200 million years ago, and that's as far back as I can go. Why? Because that's the age of the oldest magnetic stripes in the oceans. I can't go further back than that because there isn't anything older than that. And straight away, we've now solved one of our earlier puzzles. We found out why we were never able to find rocks older than 200 million years in the oceans. There simply aren't any. All the older ocean floor has been destroyed in the trenches. Well, there's another very famous puzzle which got sorted out by this. Here is the picture of what the continents looked like 200 million years ago, and it hadn't changed later than that, 250, 300, these were all still stuck together. And one of the puzzles in geology which have been around a long time is that if we look at rocks of that age, 300 million years ago, we find evidence of ice sheets. And there was evidence of ice in the rocks from India, from Africa, from Australia, Antarctica, and also South America. And this didn't seem to make any sense. Nowadays, those continents are a long way apart. What are we doing with ice in all these different places at the same time? Well, now we can see that they were all part of the same continent. On this map now, I've shown where we find evidence of ice on those continents at that time. And you can see that that ice was all part of one single great big ice sheet. And that ice sheet was centered on the South Pole, which makes a lot more sense. The South Pole is the sort of place we should have ice sheets. So that was another famous puzzle that got solved. So plate tectonics is really the great characteristic of this planet. That's what makes it special, the way the Earth's surface moves around in these plates. We can recreate what I said our alien would have seen had he come past 150 or 70 million years ago. But how does it all happen? If we think about how it happens, one of the strange things is, how do you manage to push the seafloor way back into the Earth? And we know it goes really deep down into the Earth, to 650 kilometers into the Earth, because it breaks up as it goes, and we get deep earthquakes going into the Earth like that. It can only move into the Earth if stuff gets out of the way as it goes down. And how does it do that? It does that because material deep down can flow. Now, this stuff here will flow. And yet, I'm saying rocks can behave like this, but rocks that you know about are hard. Here's a rock. This thing's slowly flowing for me. And this doesn't look to you like the way rocks behave. Here is actually a rock, which is from about 40 kilometers in the Earth, and it's very hard. I think we'd better do something about this. Let me give this back to Bryson. This rock, which comes from 40 kilometers in the Earth, is very hard and it's very strong. Yet I'm telling you that if I take this deep down into the Earth, it will flow like that potty putty. And that's because it gets hotter. And things will flow, solid, crystalline solids like this will flow, if they get heated up close to their melting temperature. This rock will melt at about 1300 degrees centigrade. If I take it down into the earth about 100 kilometers, then it will be nearly melting, but not quite, and then it will flow. And that process is called creep, and it's that process which allows the movement of these plates to happen. If it couldn't happen, we wouldn't be able to push plates deep down inside the earth. Now, I can't show you creep in rocks at the Earth's surface because they creep very slowly because they're cold. I can leave this on the table for millions of years and nothing will happen. The nearest thing I can show you to creep in a solid material is actually something quite familiar. It's ice. And over here what we have is a picture of a glacier, an ice sheet in Antarctica. And this is a picture from the air, and it's several kilometers across. And this just looks like a river flowing. Well, it is flowing, but it's solid ice. It's not ice which has melted. It is ice which is creeping by flowing very, very slowly while still being solid. Now, if we look at the plates, this is a cross-section through a plate. The base of the plate, where the interior of the Earth becomes really weak and runny and flows, is about 125 kilometers. That's what we normally take to be the base of the plate down here. And on top of this, the rocks are colder and they're relatively strong. Below this, the rocks are hot and they're very, very weak. They flow. Here, at the top, is the crust. This is the outer surface of the Earth with the surface rocks we're familiar with, which we walk around on. In the oceans, this is only about 7 kilometers thick. In the continents, it can be quite a lot thicker. But the point is that the plate is not the same as the crust. The base of the plate, the bottom of the plate, is just somewhere down here in the mantle where it changes from being cold and strong to hotter and weaker. It's not a change in rock. In fact, all the way through here, that rock is the same. It's this green rock we've been looking at. It's just that deeper down, that green rock becomes weak and it will flow. What this makes clear, I think, is that the continents, in this case, are just passengers. They're just sitting on the plate and moving with all the rest of this rock, which is underneath them. So why does it all happen? That's the next question. What's going on is that here, at the mid-ocean ridges, hot, molten rock is coming to the surface and cooling. The mid-ocean ridges are very hot places. The plate then moves away from the mid-ocean ridge, and as it moves away, it cools. It loses heat the whole time. And as it cools, it gets colder and colder and colder and colder until it gets to the trenches and it sinks back into the Earth. This is the way the Earth loses heat. This is how the Earth keeps cool. That's actually what's going on here. We know how fast this is happening from the way the stripes are separating in the mid-ocean ridges, and the fastest ridge system in the world at the moment is this one in the Pacific, which is spreading at about 10 centimeters a year. Now, that doesn't seem like very fast to you, 10 centimeters a year, but we must not forget how very, very old the Earth is. It's incredibly old. It's 4,500 million years old, and in that length of time, at 10 centimeters a year, the Pacific plate could actually go around the world 10 times. So it's really fast compared to the age of the Earth. So the great thing about this story, the remarkable thing, was that to understand the movement of the continents, which is how we started out, we had to look not at the continents at all, but at the oceans. And plate tectonics, one of the other things that plate tectonics does for us is it seems to offer an explanation for volcanoes. We get lots and lots of volcanoes at the mid-ocean ridges where this molten magma is coming to the surface. There are also lots of volcanoes at the trenches around the edges of the basins where the seafloor is sliding underneath the land. But when we look at volcanoes, let's remind ourselves what we see in volcanoes. Here's a picture of a volcano. And the volcano is spewing out molten rock the whole time. Lots and lots of lava is coming out of this volcano. And where does it all come from? We showed in the last lecture that the outer 3,000 kilometers of the Earth is solid. It is certainly solid. We are certainly not floating on a lava lake. We're not floating on a lake of magma. Volcanoes at the center of the ridges alone are making something like 20 cubic kilometers a year of liquid coming out of them. And that is enough. 20 cubic kilometers a year is enough to fill this whole lecture room in 10 seconds. And the mid-ocean ridges have been doing this year in, year out for millions and millions and millions of years. Where do they get all this liquid from? That's what we'll talk about in the next lecture. Thank you. For a booklet about the lectures or a video pack which includes the booklet, please send a cheque payable to BBC Education to BBC Education, Bankside Business Services, Unit 2A, Faraday Road, Newbury, Berkshire, RG 142AD. The booklet costs £3.50, the video pack is £29.